Hello again, this is Christopher Thrawn at Texas A&M University Central Texas, and I'm going to give you part 2 of my presentation on mathematical modeling in epidemiology. In this presentation, I'm going to introduce multi-compartment models. These are all diagrams of multi-compartment models. So in this presentation, I will explain to you what these diagrams mean. The basic multi-compartment model is called the SIR model, which was first posed by Kermack and McKendrick in 1927. SIR stands for susceptible, infectious, and recovered. So please notice there are these 3 boxes, susceptible, infectious, and recovered, and there are arrows between these 3 boxes. This arrow is labeled beta SI. This arrow is labeled gamma I. So what do these boxes and arrows mean? In a multi-compartment model, the population is divided into compartments. In other words, some people are classified as susceptible, some people are classified as infectious, some people are classified as recovered. Susceptible are people who may catch the disease. Infectious are people who may infect others. Recovered are people who have recovered from the disease. So suppose I have a population of 1,000 people, and I have 10 who are infectious, and I have 5 who've already recovered from the disease. So I would have 10 infectious, 5 recovered, and all the rest, which would be 985, would be susceptible. Now, over the course of time, susceptible people may become infectious as they contact infectious people. And this beta SI expresses the rate at which susceptible become infectious. This gamma I specifies the rate at which infectious people recover. The infection may last 5 days. So after 5 days, people recover. Now, I should say something about recovered. In the simplest model, recovered are immune to reinfection. Once I've been infected and recover, I have antibodies and I cannot get the disease again. This is a very simple model, which is not completely realistic. We will see later that we can make a more complicated model where the recovered are not immune. But in our first model, recovered will no longer be able to have the disease. This is largely the case with COVID, but it's not clear how immune people are to COVID once they've recovered from the disease, and the immunity may not last for a long time. So that's a very important unknown that people are still gathering data to understand the immunity dynamics of COVID. The SIR model describes how the population in the compartments change over time. So I would like to know how many infectious people there will be in 1 day, 1 week, 1 month, and then I can plan accordingly. I don't want to have too many infectious that will be too much for my hospital to handle. So SIR, as I mentioned, predicts the time evolution of the disease. So as I said, we have susceptible, infectious, and recovered. And these 3 curves show the process of susceptible, infectious, and recovered populations over time. So here is time, and here is population. Now, it's hard to see these numbers, but this may be 0 days, 10 days, 20 days, 30 days, and so on. And here's the population number of people. I think this is 120, 130, and so on. At the beginning, most of my population is susceptible. They have not had the disease. Maybe I have 1 infected person. Over time, that infected person will infect others. So you see the number of infections growing, and reaching a peak. This is an infection peak right here. Now, as the number of infected people grows, the number of susceptible people will go down because people who were susceptible are now becoming infectious. The number of infections reach a peak. Then as people begin to recover, the number of recovered increases. So in this case, you can see that over the course of time, most of the people start out susceptible and end up recovered. So in this case, almost everyone in the population comes down with a disease. You would like to avoid that. You would like to prevent the disease from spreading through the whole population. Sometimes that's possible, sometimes that's not possible. Here you also have this peak. You do not want this peak to be too high. If this peak is too large, you may have too many people for your hospital, and many people will die. Those are important things to realize. I will talk later at what I mean about herd immunity. Basically, if there are many people who are recovered, then the disease level can be, we'll talk about those concepts later. Now, here's a data set gathered from New York City. This is actual New York data, and it shows the total number of cases from March 2020 to October 2020, and you see how the cases are rising. And here you see the infections per day. Now notice this is very, very close to this mathematical curve here, where you have an infectious peak and you have the recovered who have herd immunity. You also see in this case a very sharp peak, and you have a curve that's growing and then gradually becomes flat. So you see that the mathematical model is giving me behavior that resembles the real behavior. The New York City death rate is 33,000 deaths in 500,000 cases. That's 6.6%. This is one of the highest death rates in the world. This was a case where COVID had caused very great damage to the population. Here's another curve, COVID cases in Texas, which is my home state, also from March to October 2020. We have a similar graph, the number of cases and the date. Here we have a case where the infections go up. Here the peak is much flatter, and then it smooths out and it lasts for a long time. It looks like it may be growing again. So here we have the total number of cases, which gives me the recovered, and so I'm getting more and more recovered, but the recovered is still growing. So I have not reached a flat peak. I have not leveled out yet. Okay, so it looks like we have not reached the stage of herd immunity. We are still going up. However, the peak number of infections was much less. In Texas, we had 18,000 deaths in 900,000 cases. The death rate was 2%, much lower than in New York City. So there are several reasons for that, and we will talk about that later. Okay. Now, in my model, I talked about the compartments, susceptible, infectious, and recovered. I also have these two numbers, beta Si and gamma I. So I'm going to explain what these numbers are in this slide. So individuals move or transition between compartments over time. Someone who starts susceptible may become infectious and then may recover. Each compartment here represents a number, and these numbers change over time. And I want to have a mathematical model that explains how these numbers change over time. These transition rates here and here tell the number of individuals per day that move between compartments. So in other words, if I know S and I and beta, I compute the product of those three, and that will tell me how many susceptibles will become infectious at that day. Now S and I are changing, so the number of susceptibles that become infectious on a daily basis changes over time. Similarly, if I know gamma, which is a fixed parameter, and I multiply by the infectious, which is I multiply those two, I will know how many infectious people are recovering per day. So transition rates tell the number of individuals per day that move between compartments. Now these rates are proportional to population sizes. The larger the number of susceptibles, which is S, then the larger this rate. The larger the number of infectious, then the larger this transition rate. This makes sense. Of course, you would think that the recovery rate, this rate, should be proportional to the number of people. The more people you have, certainly the more infectious you have, but a certain proportion should recover every day. So these are called proportionate rates. Now here we have beta Si. I can think of this as beta I times S, the number of susceptibles. So beta times I is called the force of infection, and gamma is called the recovery rate. Just to make it very clear, S is the number of people in susceptible, I is the number of infectious. There's no transition from recovered, so I don't have R in my transition rate model. So how to calculate the force of infection? I want to have some idea how to calculate these parameters. Now S I would be able to get from the number of susceptibles in the population. I also, the number of infectious. But what is beta? How do I compute this beta? So think about the situation this way. Each susceptible person contacts a certain number of people per day on the average. So we call that the contact rate, C. Suppose on average one person contacts 10 people per day. Now contact means contact close enough to transmit the disease. So this is an average number. Of course, not every person will contact exactly 10 people, but all we need is an average number of contacts per day. So we call that the contact rate. I'm going to use C to denote this contact rate. Now, a certain fraction of these contacts are infectious. I should say infectious here. The infectious proportion is equal to I over N. So out of these C contacts, a proportion I over N will be infectious. So in other words, if I contact 10 people per day and 1/5 of these people are infected, then that would be 10 people times 1/5. On the average, I would contact 2 infectious people per day. Now, of these 2 people who are infectious, only a certain fraction of contacts will produce the disease, and that's called the transmission rate. So, as I said, suppose I have 10 contacts per day, and 1/5 of people are infectious, and then suppose only 1/2 of the infectious contacts will produce the disease. Again, these are all average numbers. So that's C times I over N times T. That's why I have here contact rate times transmission rate divided by N. It gives me my beta. So the number of new infections is going to be S times the contact rate times infectious over N times T, which I can group these 3 parameters together, and that will form my beta. All right, that's how to compute this force of infection. Now I want to compute the recovery rate. Again, we're going to use average numbers. The period of infection is usually D days. So we can get this from data. Now some infections may last more, some may last less. So for each time period, about 1/D infectious people recover. Now I should say something about the difference between infectious and infected. I really am interested in the infectious because the infectious are the ones who are going to produce more infections. So that's why I should say infectious here instead of infected. If someone is still sick but not infectious, I would still call them recovered. So each time period, about 1/D infectious people recover. So that means my rate of transition, my rate of recovery is equal to 1 over the average period of infection. So that explains these 2 transition rates in the model. Now there's some simplifications because these are average rates and not detailed rates. So we'll stop here for this slide. In the next presentation, I'll tell you how to construct a simple model using Excel.